Everyone, in this video we'll be discussing some basic concepts of heap, namely what is a heap, what are the properties of heap, and the concept of nodes height and heap's height. Okay. So first, what is a heap? So a heap is first of all an arrayed object, and second of all, this array can be represented as a nearly complete binary tree. So let's unpack a little bit more each of these statements. So the first statement, heap is basically an array object, a list of ordinary Python. Here's an example of a heap. So it's just basically an array. This array has two attributes. The first attribute is a.length, the length of the array. In this example, our array has length of 10, and therefore a.length is 10. And the second attribute is the heap size. That is how many elements we would like to include in our heap. This number can vary anywhere between 0 and the length of the array. So the first attribute, a.length, is clear enough, but we'll understand more about the second attribute when looking at the tree representation of heap. As we have said earlier, this array object can be represented as a nearly complete binary tree. Here's how that's done. Hopefully by the end of this, you will be able to understand what a.heap size is for. So we'll reuse the earlier array example here. And the first element of the array will be the root of the tree representation. The next two elements, 14 and 10, will be the left and right children of the first element. Then the next two elements in the array become the children of the second element. So 8 and 7 become children of 14. And we do likewise with the next two elements. 9 and 3 become the children of 10. And so here, in this specific heap, the value of a.heap size is 7. Since the heap here contains 7 elements, and you will see this heap size attribute becomes very handy later on when we study different operations supported by a heap. Now the question is there a more systematic way to determine the left and right child of a given node without explicitly translating the array representation into the tree representation? Now let's take a look into the tree representation of the heap that we just built. So as with many other things, we start with a concrete case and then generalize our observation into a formula. So we first number the index of each tree's element from 0 to 6. You can see from here. Note that in the Corman textbook, the author indexed everything from 1 to 7, but since we'll be coding in Python, so I think indexing from 0 to 6 would be more straightforward. And so we can see that here, the left child of 0 is 1, right? So left child of 0 is 1, and the left child of 1 is 3, and the left child of 2 is 5. So I wrote here. So the general formula for the left child's index given its parent index is 2i plus 1, right? So the 1 equal 2 multiplied by 0 plus 1. 3 equal 2 multiplied by 1 plus 1, right? And 5 equal 2 multiplied by 2 plus 1. So we're good for the formula for the left child. And so we proceed similarly with the right children, and we can easily figure out that 2i plus 2 is the general formula to figure out the right child of from a parent's index. So far so good. Now let's recap what has been discussed so far. So first of all, heap is an array object. This array object can be represented by a nearly complete binary tree. The index of the left child can be computed by this formula, 2 multiplied by I plus 1. And the index of the right child can be computed using this formula. But can every array be a heap? To discuss this, we first need to introduce the heap property. There are two kinds of heaps actually. So the first kind of heap is max heap and min heap, the second kind of heap. In a max heap, the value of the parent is always larger than or equal to the value of its children. So as a result, the largest element in the array is always at the root of the tree. Our earlier example now turns out to be a max heap. Here you can see that 16 is bigger than both 14 and 10. 14 is in turn bigger than both 8 and 7, and so on and so forth. Conversely, in a min heap, the value of the parent is smaller than or equal to the value of its children. Straightforward. Now let's move on to discuss the concept of height of a node and height of a heap. The height of a given node is the number of edges on the longest path from that node to a leaf. And the height of a heap is simply the height of its root. Okay. Now let's look at our example. In this heap, the root has height 2, right? Because the longest path from this root to the leaf is 2, right? Number of edges. So there are 2 edges here, and of course the heap, the leaves of the heap would have height 0. Unlike height, depth, which you might remember from when we learned about recurrence trees, depth will go in the opposite direction. It means that the root will always have depth 0, and the leaf will have the deepest depth. And so depth and height, they go in opposite direction. And lastly, the height of a heap with n elements will be log n. Why is this? Now I'll leave you to figure it out. And so this is it for our overview about heap. See you in the next videos for the heap operations. And as always, please feel free to let us know if you have any questions. Thank you.